All right. Let's see. As you know, the second homework has less time for you to work, simply because I want to be sure that we at least cover 6 homeworks. Now, I notice some of you don't bother about homeworks because you are auditing the class. Disappointed to hear that. Okay. A recommendation, when we post homeworks, keep revisiting them, because when I get comments from students or when I look back, I go directly and do changes there. And I don't want to keep sending messages saying we changed this and that. So please, look on the website for changes. Okay, so we talked about the elimination algorithm last week, both for directed and undirected graphs. And today we want sort of to revisit the elimination algorithm, but put it on a form that is related to what's called message passing. And the algorithm that goes with this name is called the sum product algorithm. In essence, it's the same sort of as the elimination algorithm, but a little bit or way more efficient, depending on what type of graphical model you have. So we're going to apply this first to trees, and then next week we will extend it to general graphs. So actually, when we apply this to trees, we will see that these algorithms are really exact inference algorithms. So there are no approximations to be done. All right. So let me bring up some of the basic ideas we have seen with the elimination algorithm. So here is a directed graph, 5 nodes. This is the decomposition of the joint, the factorization of the joint applied by the graph. And let's say that the inference task that we're interested is to compute the probability of A given that capital C is little c. Okay, so so this is the problem actually we have discussed up to now for several lectures. So obviously, you can start computing this conditional using this factorization, and this is going to be a lengthy process. So let's see how you're going to do this with 20 operations. So to compute this, you will need to compute the joint of A and C, divided by the probability of capital C being little c. To compute the joint of A and C, C is an evidence here equal to little c. Obviously, you're going to have to take this joint distribution of A, B, C, D, E, and marginalize out B, D, and E. So you have to perform this operation that you see here. And if we assume that these variables are all binary, you will need 2 terms for B, 2 terms for D, 2 terms for E. So 8 terms, and you will need to compute these 8 terms for each of the values of A, which are 2. So this calculation is 16 operations. Okay? So this is what you see on the, the numerator here. To compute this, you have to do a marginalization on A, okay? So that's 2 operations. And to compute this ratio, you have to compute this for every value of A, another 2 operations. So if the calculation count is correct, you need 20 operations basically to do this right. So the more efficient method, based on the elimination method we discussed, is to actually compute this by pushing forward some of the summations. And now you notice I put the summation on E on this term, the summation on D on this term. All these terms come from the factorization of the joint. And by a magic, because these are conditional distributions, this term is equal to 1, this term is equal to 1, and the only thing you have to compute is this summation. All right? So 2 values of B, and you have to compute them for 2 values of A. This is only 4 operations, and if you look back, this was 16 operations. All right? So basically, the elimination algorithm that we have seen up to now allows us to compute these marginals, things like this, in a way more efficient way than just doing, marginalization using this factorization implied by the graph. All right, so 20 operations. If you don't do anything special, if you use the elimination algorithm for this directed graph, you only get this in 8 operations. 8 operations because this is 4 and the other 2 steps are basically identical as the previous graph. So there is a problem with these algorithms, with the elimination algorithm, and the problem is that we focus on calculating one marginal or one conditional distribution at a time. All right, so in this problem, if let's say your objective is to calculate, I don't know, the probability of B given C equal to little c, you're going to have to repeat this from scratch. That's waste of time. So the algorithms we will discuss today is how do we compute not just, let's say, one conditional or one marginal, but all conditionals or all marginals in the graph, all at once. So given the evidence, what's the conditional distribution of all the other nodes? Okay, one at a time. Can we do this more efficiently without having to repeat this for every case? In principle, can we do some calculations that can be recycled as we compute one marginal or one conditional at a time? Can we recycle some calculations? And the algorithm that we will discuss today is basically a subcase of what is called belief propagation methods. Okay? But today what we will see is exact belief propagation in trees. Okay? So you will see mathematically there is really no new techniques on what we will discuss, but the algorithm is way more efficient than the elimination algorithm. So any questions with what we have seen up to now with the elimination algorithm for directed or undirected graphs? Okay? So somewhere I think I have a repeat of the algorithm again, but we will see this as we go. So the idea is to, you remember when we did the elimination algorithm, we calculated a lot of intermediate factors. So the idea is, can we reuse those intermediate factors to compute multiple marginals at the same time? And we will do this today, but only we will do this for trees and tree-like graphs. Okay? If you try to do this for general graphs, basically the algorithm needs a lot of modifications, and the algorithm will go, the general algorithm, under the name junction tree algorithm. Okay? And we will discuss this next week. So right now we will concentrate on trees and tree-like graphs, and we will see why that. So let's motivate what's going on with a little chain. So let's say we have the joint distribution of x1 to xn, and we want to compute the marginal distribution of, let's say, node xn, but we want it to compute in a way that will allow us at almost no additional cost to compute the marginals of the other nodes as well. So we're going to do this calculation in a little bit more efficient way than we have done before. So P of X, I am taking the maximal clicks here are 2 of order 2. So I write P of X as this undirected graph is a potential of the nodes 1 and 2, 2 and 3, n minus 1 and n. And because these are not probabilities, I use a factorization. I use a normalization factor C there to take care that this product basically 1 over Z gives me a value probability distribution. All right, so this graph in the equation below, it's sort of an elimination algorithm, but very much different from what we have seen up to now with the elimination both for directed and undirected graphs. So I want you to look at this equation and tell me what is different. You notice I have 2 terms, one on the top and one on the bottom. All right? And I remind you, P of xn means I have to integrate on all variables but xn. And this is what I have done here, but I have done it in some specific order. So I want you to tell me what is you see special there in the order and how is that different from before. So the node xn is somewhere, let's say, on the middle, somewhere there. It doesn't have to be in the middle, but it's somewhere in between. So in the first summation, I am starting summing from the right to the left. So I'm summing from x1 to x2 to xn minus 1. So I am propagating information from x1 all the way to xn. All right? And look now at the summation on the bottom. I have rearranged it in such a way that I first sum on xn, then on x capital N, then x capital N minus 1, all the way to xn. So I propagate information from x capital N to xn. So I propagate from the right to the node xn. So there is a forward propagation of information to node xn, and there is a backward propagation of information from the last node x capital of n. Okay? So this is not similar to what we did with the elimination algorithm, right, where we start eliminating with some order. Here, we are sending messages from the left, and we're sending messages from the right, and I'm going to define what these messages are. And actually, the definition to start with, the message that is being sent from the left to node xn is denoted here mu alpha of xn, is a function of xn, is basically is the product of all the potentials to the left of the node xn, where all the other variables but xn have been summed out. Okay? And mu beta is the product of all the terms to the right, where everything has been summed out from xn plus 1 to x capital N, except little xn. Okay? But it is not just simple definition here, right? This definition implies that the summations, this calculation, happens in the proper way that you see here, that implies some recursive relations for these messages, mu alpha and mu beta, and I'm going to write those recursive relations in 1 second. Okay? So look carefully at these equations, right? We define this to be mu alpha, and I denote it here. Is basically, we call it the message that is sent from the left, that's alpha, notation used by Bishop, to the node xn. And mu beta is the message sent by the nodes to the right of xn, okay? And the definition is what you see here. And the marginal comes to be basically the product of mu alpha times mu beta divided by the normalization factor of z. So effectively, if you want to calculate with this definition the P of xn, what you need to do is calculate this message mu alpha, mu beta at xn, and then multiply them and normalize them, and you're done. So before I change slide and I give you the recursive relations from mu alpha and mu beta, can you guess? Can you guess the recursive relation? You can see it here, but what I was going to ask you, can you guess how this algorithm can reuse information that the elimination algorithm could not do? I mean, look at this, the way that this message is we denote this message like that, right? So mu alpha, but also I put a similar definition of mu alpha xn minus 1, which will be the product of all the potentials from the left, all right? So as I go forwards from x1 to xn minus 1, with all the variables eliminated, but xn minus 1 left only, okay? So can you see a way where somehow this algorithm will be way more efficient than elimination algorithm and will allow me, using this idea here, this derivation, to compute the marginal of all the nodes in the graph. Not one, but all. What will be the new algorithm that we can think about? In other ways, if my interest is not the marginal of xn, but the marginal of xn minus 1, according to this derivation, how do we compute the marginal of xn minus 1? According to this, what will be? I put some of the errors here, right? I haven't put all the errors there. So how do we compute the marginal of xn minus 1? Will be mu alpha, of, which is a function of xn minus 1, multiplied with mu beta of the message that goes to xn minus 1 from the right, which is an arrow that will be a message that goes this way. Correct? So what is the algorithm? How is this algorithm going to come to be more efficient? What the algorithm is going to be like that will allow me to compute all the marginals at once? Well, the algorithm will be compute all the messages forward from left to right, compute all the messages backwards from right to left, and then basically you go at any node and you actually can compute the marginals by multiplying the messages arriving at each node, the alpha and beta messages. And the normalization factor, how many times do you have to compute it? You notice here that I did not put Zn or anything like that, but the normalization factor, how often do you have? The normalization factor actually comes, from where it comes from here, from the joint. So how many times, the normalization factor, let's say for this case, will be take this product, sum it up for all values of xn, that's z. So how often do you have to compute z? Like, will it be another normalization factor for xn minus 1, for x1, x capital N? No, so z is computed once. Okay, so what we need to do now is we need to see if this definition of mu alpha and the definition of mu beta can be written down in a way that is sort of recursive, so we can have a nice algorithm. So look, let's concentrate on mu alpha, right? So so the mu alpha here is all the this summation of everything except xn of all the potentials to the left of xn. Okay, so summation of xn minus 1, and somewhere here there will be summation of xn minus 2, etc. I want you to think visually, all right, looking on this definition. Here I'm going to have summation of xn minus 2, then xn minus 3, and then x1. Can you tell me that summation, starting from xn minus 2, what is that? What's the name of that summation if the name of this is mu alpha of xn? It will be mu alpha of xn minus 1. So basically, the recursive relation for the alpha messages, all right? So if you want to compute mu alpha of xn, what you need to do is sum of xn minus 1 of the potential that joins xn minus 1 and xn, which is this. You remember here, that's that potential, times that summation that you told me, starting with xn minus 2 all the way to x1, and that's the message mu alpha at xn minus 1. Very easy actually to visualize. No equations. I actually, when I look at this, right, I don't look at the equation, because to compute this message is really the message that comes in, which is mu alpha at xn minus 1, times this potential, and then x1 has to be integrated out because mu alpha is a function of xn, and that's it. Okay? And similarly, if you want the message mu beta recursive relation at xn, will be the message coming on from the right, function of xn plus 1, times the potential of xn plus 1, and then you integrate out xn plus 1, and that's the recursive relation. Okay? And these are the Chapman-Kolmogorov relations that sort of appear not only in the context of belief propagation, but many other areas in mathematics. For those who are have studied dynamic programming, sort of these are the standard equations you look over at dynamic programming problems. Someone may ask, wait a second, this recursive relation requires, for example, to know messages at the edges. So how do I calculate the message that x1 sends to x2, mu alpha at x2? So the idea here is, the only thing you left is the potential psi1, 2, right? There's no previous message arriving at node 1, and then what you need to do is integrate on x1. And similarly, if you want to find the message that x capital N sends, basically you have to integrate x capital N from the potential psi of xn plus 1 xn minus 1 xn. Okay? So a similar relation to what you see here. So this is sort of your boundary condition, and another boundary condition for the node xn, and then recursively you compute all the messages. You compute all the messages, then you have everything. You have all the marginals. You can do anything you want. All the information is inside those messages. So think of these messages, right? If some of these nodes, for example, are evidence nodes, it's basically information that propagates from these evidence nodes to the query node, in this case is xn, okay? And somehow, what is interesting, okay, and you may want to think this way, the marginal of each node is this product of the messages that are coming, right, from the left and the right, define somehow what the status of node xn is, okay? So effectively, you have belief propagation, if you like, from x1 to xn, and belief propagation from x capital N to little xn, and those two messages define the state of the node xn and its marginal. All right. You can do actually a lot of trivial calculations, and do we give them any homework on this? On this one, no? All right, start writing, okay, for the next one, massive homeworks, all right? Okay, so here is a trivial calculation. And let me go back. Suppose somebody tells you, I want to find the joint probability distribution of any two arbitrary nodes. I mean, so don't look at the equations, don't look at the nodes, right? But suppose, I give you two nodes and I say, find me the joint distribution. What did you do? I mean, how just thinking of these messages that define the state. Now you have the joint. What do you think is going to be happening? You can take the nodes to be next to each other, far away. It doesn't really matter. But if you want the joint of two nodes, what do you think is going to be the actual result? So in this case, what I have you is the joint of xn minus 1 and xn, okay? So is the message coming from the left to xn minus 1, the message coming on the right, times the potential between the nodes xn minus 1 and xn. Actually, if you don't believe me that this comes in, right, what you need to do is start with your elimination. Eliminate all the nodes to the left of xn minus 1, eliminate all the nodes to the right of xn, and what you get, the first you will get, the only thing you will not eliminate is the potential between xn minus 1 and xn, all right? The summation on the left will give you this mess, the summation on the right will give you that, and there is the answer, okay? And you can do this, you can do lots of these fancy thing. So if you want to compute joint distributions, the information is encoded on these messages. The idea is everything is encoded on these messages. Once you have these messages, whatever query you have, you can resolve it. So the calculation, by the way, to do all of this, if each variable can take m values and you have n variables, so is two stands because you have to calculate messages coming, the forward messages and then the backward messages. The calculation of each of the messages is basically m squared, and you have n nodes, so nm squared, so the cost is 2 times nm squared, and the important thing here is linear in n, and this is what you're interested in. Okay? Any questions with this algorithm for chains? Obviously, you can imagine that this can be generalized to trees, right? So we will see how it works with trees a little bit. It's not tricky. It's the same idea more or less, and the notation is the same. But chains is the easiest way to see what's going on. So now, if you have evidence, right? How do you account explicitly for the evidence? And the answer to that question is, it's actually the same way as what we have done is so in this case, let's say you want to compute not the marginal of xn, but let's say the conditional of xn given x capital F. So let's say our evidence is x capital F, okay? So the only modification you have to do is, if you like, is in the boundary condition of the message that x capital N sends to xn capital N minus 1, which is this message. Before we said is the potential of xn minus 1, xn. You remember the boundary condition? Instead of this, what we had is we had summation over all possible values of x capital N. Now there's no summation of x capital N. We fix x capital N to whatever value the evidence has. Okay? So the only change in the algorithm is instead of summing over the values of x capital N, all right, fixing x capital N to the specified value. I mean, what actually you can do is you can put, you remember our evidence potentials there? You can put a delta function and then do go and sum on x capital N, but the only value because of the delta function will give you will be that, and that is sort of the same idea. Okay? So the calculations of the conditionals given this evidence, it's exactly the same thing as for the marginals. Zero change in the algorithm. Messages coming from the left and the right. The only difference is that in the message propagating from the evidence here, you have to change some of your boundary condition in this case. All right. I am not going to do this today, all right, but I want you to, we're going to spend actually a whole lecture on this algorithm, but I want you to see it, early on. You can actually, instead of doing the summation and computing marginals, somebody will tell you, in this chain, can you find us the mode of the joint distribution? In other words, can you find what is the x max that maximizes the joint distribution that's very high dimensional? Very important problem. All right, you have all these variables defined on the chain, and you want to find the mode of the joint distribution. So before we had the summation, all right, and for example, in the context of the elimination algorithm, right, rather than summing on the different variables the way we had it, now what we need to do is take the factorization of the joint and push all the maximizations first on x capital N, then xn minus 1, all the way to max small xn. So we need to find an efficient algorithm of doing this, sort of by doing calculations forwards and backwards, and that will lead to a very famous dynamic programming algorithm, which is the Viterbi algorithm. Okay? So we will do this for hidden Markov models. We'll spend one lecture, all right? But I want you to see that somehow The summation can be replaced with maximization. The algorithm is sort of the same, but there is some details that they are unique to this Viterbi algorithm. And they are unique because, you know, you have to maximize here the joint, not the marginals, all right? And the way you do this, introduce some little tricks that someone needs to consider at the end of the day. So this algorithm goes under max product rather than sum product, and we will revisit. Okay. So the sum product algorithm that we just discussed for chains, it can compute all the marginals for trees, all right? And I'm going to show you again pictures, all right? Are all undirected graphs, are all directed graphs leading to trees? What do you remember when we worked with directed graphs, we had some, even in the elimination algorithm to make them undirected. So when we make them undirected, we always get trees. What do we need to get a tree in a directed graph? It has something to do with moral events in life. If a node had two parents and we transform this to an undirected graph, what was happening? We will get what? If you have a node with two parents, right, and you transform this to undirected, what do you get? You get the moralization effect, you get a loop. So it's not a tree anymore, all right? But if every node in the directed graph has one parent, then you do actually get a tree, okay? Now, if in the case of a directed graph that a node, let's say, has two parents that you marry and you get a loop, right? You can actually transform that undirected graph to what is called a polytree. And it comes out using this concept of factor graphs that I left behind on my previous lecture. You can, if you transform then the undirected graph to what is called a factor graph, then you do get a tree. My point here is that the sum product algorithm can handle all of these things with the same complexity, all right? So learning on how to do inference message passing with trees is very important because it's applied to both directed and undirected graphs. I'm going to show you the things we discussed today with pictures, okay? So this is an undirected tree, okay? Here, every node has one parent, so this is a directed tree, and if there's no moralization, so it leads to something like that, okay? The only thing that I emphasize here in blue is here, in the directed graph, we work with conditional distributions, right? These are the potentials. They're conditional distributions of a node given its parents, and these distributions are normalized, but when you work in undirected trees, all right, there is a normalization factor in general, okay? So in general, there is a normalization factor. Even in this case, if you have some evidence and you transform this to an undirected tree, then there is still a normalization factor. The fact that you have an evidence basically introduces a normalization factor so that you need to account for. All right, and here is the case of a polytree. So this guy has two parents, so if you marry them, you connect them together, you create a loop, right? So this is a polytree. So we will learn, I think, on the lecture tomorrow, so I don't forget we're going to have a lecture tomorrow. We're going to extend the ideas today to see how we're going to do inference on a polytree using factor graphs. Okay, so we're going to apply now this message passing to very general trees, okay? And I'm going to work with both directed and undirected graphs, so I need to remind you some of the notation. So let's work for undirected trees, and what I have here, this is the tree, and I have potentials for every node, and I have two pair potentials. Now the potentials at every node, you can think of them evidence potentials, for example, right? These self-potentials, you don't, in general, you don't need them because the clicks here, what's the maximum size of the clicks here? 2, okay? But, if you can think, right, that this somehow was derived by a directed graph, then you will have the probability of the nodes, and those will correspond to these self-potentials. Or if you can imagine, if one node is prescribed, this will be the evidence potential. So it's always good, in addition to these pair potentials that you have for the tree, to plug in also the self-potentials for every node. Okay? So in an undirected tree, this is the general expression. Okay? This is not an approximation. These are the maximum clicks. You have potential of 2 nodes, and these are the self-potentials. Now, if this was the directed tree, things are a little bit easier, because in the directed tree, what you do is you start with the probability of the root node, and then you have the probability of the nodes given the parent. Okay? So effectively, if you want to take a directed tree and transform it to an undirected, you can see the one-to-one correspondence between these probabilities and these pair potentials, and easily you can make this to correspond to that. How is that? You can say at the node R, make this potential psi xr equal to P of xr, and make all the other potentials equal to 1. Okay? So basically this is a very general expression for both directed and undirected trees. Evidence, basically the only thing you have to do, if let's say the value of xi is fixed at xi bar, you need to change the definition of the self-potentials. And so if the node is not an evidence node, this potential is what you're starting with. If it's an evidence node, you just have to plug in this delta function that basically says the value of this xi, you only get a non-zero contribution when xi is equal to xi bar. So if you have evidence, the previous equation that I had, this is, the joint. Now if I want to write the probability of x given the evidence, the expression is the same. These are the self-potentials for each node, but they are the evidence potentials, these modified potentials. But what is important to notice, when you have evidence, the normalization factor now may not be 1. So even if this graph was derived from a directed graph where everything is normalized, so you notice in this case, when you talk about directed trees, these are normalized probabilities, so z equal to 1, but when you have evidence, the normalization factor is not 1. So in some cases, in problems with evidence, it doesn't really matter if you have directed or undirected, because the degree of complexity is the same. Just remember that this normalization factor is not 1. Okay. Don't need this. We don't need this. All right. So let me remind you, before I start the algorithm, on some sort of not esoteric things, but sort of common sense things that usually you don't see when you program this directly. Suppose that the actual potentials, right, were coming from a directed tree, and in directed tree, the distributions we work with are the probability of xj given its parents. So let's say the parent here, there's one parent because it's a tree, it's xi. Suppose now we have a query node here, and we start eliminating nodes from the bottom, okay, from the leaves. Will you agree with me that if I start summing on node xj, so eliminating xj, that this will come equal to 1? Right? So xj is here, if you're interested here, you start getting rid of xj, it will disappear because it's equal to 1. Okay? All right? So in assuming that you have no evidence in this unconditional case, you arrange things so that these nodes that there's no evidence, basically you can eliminate them before you reach your query node. You know what that means is, if I am interested in what is going on here, and I have a lot of nodes with no evidence down here, what can I do to those nodes? If I'm interested to figure out the probability of this node in a directed graph, and I have a lot of nodes below, but they are not evidence nodes, what can I in principle do to those nodes, considering that this is the case? We can prune them, we can get rid of them, because they will not contribute anything. And you know what that means? That is actually, if I'm interested in what is going on here, and down here I have the leaves, right, in the ordering of elimination, it will only make sense to assume that the leaves are what type of nodes? Here, if the nodes are unspecified, are not part of the evidence, will disappear, will be pruned out. So the only thing we need to consider is when the leaves are what? What type of nodes? Evidence. Okay? So we only have to consider the case where the leaves are basically evidence. Okay? In that case, you remember that normalization Z that we will consider is not going to be equal to 1. So we can prove any subtree that contains only variables that are not conditioned on by eliminating backwards. Okay? So let's see now what happens. Okay? In a case like this, I am claiming, if this is my evidence node, that somehow these trees, I can prove them and I can do inference on each of them separately. So I want you to tell me why is that the case. You don't have to read what it says there, because I don't have time for reading, right? So this is my only evidence, right? Here I'm not implying that you're not going to account for the changes, let's say the potentials, because of the evidence, but why I can actually separate this to 3 trees where I can do inference separately. What is there fundamental on this graph that allows me to do that? For example, with this evidence here, what can you tell me on the probability of this node conditioned on this? I mean, conditioned on the what can you tell me about the joint probability, let's say, of this and this condition on that? They are independent. Okay? So effectively, the only thing you really have to consider is anything that is unobserved, right? You prune it away, all right? And the only nodes that you're going to have in the leaves will have to be evidence leaves, and everything else basically has to be unobserved that you will be interested to do inference, okay? So there is lots of things that I said there, but some of them basically are sort of common sense coming in the context of the direct graphs from this relation. There's no point of doing summations that they are equal to 1, so what you need to do is prune leaves that are basically unobserved. And if you have evidence, you have to be careful, you know, because evidence splits the graph, and then you may be able to have inference in, like in this case, with 3 different graphs. All right. So we're going to start doing message passing on trees and generalize the algorithm we saw on a chain. So this now will be on a tree. Does anybody, our field from computer science, know what's the post-order elimination? I mean, we're going to have to do some elimination of the nodes, right? And one way or another, if it's a tree. I'm going to give you an algorithm when we finish the lecture today that defines post-order. But in this case, the post-order is you start basically from the left subtree, which is this, and you start from the left to the right, so 4, 5, 2, 3, and 1. Okay? So obviously in every subtree you have to start from the childs, but always from the left. So 4, 5, 2, 3, and 1. okay? I gave you a reference there if you want to click it, but I'm going to give you the algorithm, and all of these algorithms that you will see on trees, they're all recursive. So I don't know if you ever programmed anything with recursive algorithms, but sort of you need to get used to when you do sort of message passing algorithms. Okay, so let me, we have a post-order elimination order, and I'm going to give you a message passing version of the elimination algorithm. So let's say that we're interested. We have evidence of nodes x2 and x4 and x5, all right? And somebody tells you, compute the conditional of x3, okay? So basically what we need to do is we need to integrate x1 here, all right? So let's, the factorization here is my self-known potentials, which are basically these modified evidence potentials we introduced before. These pairs, xi, xj, because my clicks are maximum size is 2. So I am writing this in a directed graph. So I have potentials for psi e for x1, x2, x4, x3, x5, and I have the potentials x1, x2, x1, x3, x3, x4, and x3, x5. So what I have done here is x2, x4, x5 are given, all right? I don't need to do any modifications. The only modifications are inside the definition of this psi e, right? So there's no need to sum on x2, x4, x5 with a delta function because this is already done inside psi e. So the only thing I have here is a summation on x1, all right? A summation on x1, but below the summation you see some definitions, and I want you to look carefully on what these definitions imply in the context of eliminating nodes one at a time. So let's look at this last term, okay? So we're interested, if you remember, the conditional of x3 given this evidence, okay? So the last term I see it says the self-potential of x5, right? And then the potential of x3 and x5, okay? Now, the reason there is no summation on x5 here is what again? Why there's no summation on x5? Because it's evidence, okay? There is a delta function that will force x5 to be x5 bar there, okay? Again, if you want to put explicitly and put a delta function there, it will take care of it, but, you know. All right, so can you tell me just physically, what is this product you think doing for us? Is psi of x5 times psi of x5 comma x3, okay? I denoted this m with subscript 5,3, and it's a function of x3, because x5 is just a constant. So what is that? If we are going to put some words to define it, what is that psi e of x5 times the potential of x3 and x5? What is that? I mean, obviously m stands for message, so what is that? Is the message x5 sends to x3, okay? And basically, you know what it is? It is evidence propagation from below to node x3. The fact that x5 has some value implies something for x3, and that implication is contained on this message. So it is really, you know, belief propagation, okay? Similarly, the second term, psi of x4 times the joint of x3 and x4 is this message from 4 to 3, okay? So this is a message passing from x4 to x3, so evidence from x4 propagates to x3. Similarly, a message from x3 to x1, which is this, all right? So I'm rewriting this equation now. There is no summation on x3, so this goes outside, and there is summation on x1. These terms depend only on x3, so I don't touch them. And there is this summation on x1, so let's look what this is. Very carefully. It says, take the evidence on, so we have to sum x1, okay? So take the evidence of node x1, all right? Take the potential of x1, x3, and take the message that is propagated to x1 from node 2, and then get rid of x1. So I want you to remember when we discussed about chains, and we had the recursive, this Kolmogorov relations, and we said the message this way, it is the potential times the message coming in, and then you integrate the previous variables out. So look at this. It says here, if I call this M13, it says M13 is the potential of x1 and the potential x1, x2, times the message coming from node 2, and then integrating node 2 out. The only thing that is actually a little bit different from what we had before is that now we have included the self-potential nodes that we need to carry them on, right? But if for whatever reason you wanted, you could integrate those inside the spare potentials as well, so the equation will look identical. But again, the recursive equation says is to find M13, which is a function of x3, integrate on x1, the self-potential of this node, the joint potential of x1, x2, and the message arriving on node x1. So the message that basically propagates, it is the message coming in times these potentials with x1 eliminated. Makes any sense? A little bit? And again, it is, you know what, if you look at the equation sort of looks, you know, not complicated, but, you know, you get a much better sense if you look at the graph, right, and you say, look, information propagates from the evidence to node x3, but the information to propagate, it has to first go to node x1. How does it do this? With this message M21, okay, which is this, and then information has to go from node x1 to node x3, and this is the message M13. How do you get M13 is by eliminating x1. And how do you eliminate x1? You multiply the potential of x1, the joint potential x1, x2, and the incoming message. Because all the messages from the evidence need to be propagated through, right? And so to get M13, you have to compute M21, which also implies that this calculation of messages has to be done in the order of elimination of nodes. You cannot go in other ways and calculate M13 before calculating M21, because you will not have enough information to do the calculation, okay? However, I can calculate the message from x4 to x3 at the same time as I calculate the message from 2 to 1. So actually, you can do all of this in parallel, right? But you need to basically have a scheme that says you can only propagate, you can only calculate the message when at the node, so you can propagate, let's say, a message from node 1 to 3, only if all incoming messages to node 1 are already there. This is like doing parallel programming, right? And you say, you know, I can only start executing and sending information somewhere else if all the information I need is here, has arrived. And that information here is this incoming messages, okay? All right. So a very general algorithm now, practically identical to what we discussed for trees and what we described, you know, the last 5 minutes. So let me define. So, you know, here is, all of these are circles actually. I don't know why they look here like ellipses, but so all of these are nodes, okay? So let's say that this is somewhere up there, the root node. This is node I, and this is J. And we want to compute the message J sends to node I. So the message J sends to node I, again, don't look at the equations, right? It will be the self-potential of node J, right? The joint potential of nodes I and J, and the product of all the messages arriving to J from all of its neighbors except node I. So are all the messages that arrive from below, and then you sum of J, which means you eliminate J. Okay? So summation in J of the self-potential of Xj, the joint potential of I and J, and all the messages arriving at node j from below from all of its neighbors except I. You're not going to send to node I a message you receive from I. And actually, that's a very philosophical statement. And if you're interested, I can give you information to read about it. All right? So in other ways, you may like to make yourself feel good and send messages to yourself, but that actually you have a problem, mental problem. Okay? Let's not philosophize because that's not a good territory to be. Okay, any questions about this? It actually, the algorithm does, can you tell me what's the difference, all the difference from the chain algorithm that we saw before, right? Just one big chain. So look at this and tell me what is different from before. Every single term that looks different. What is different here, for example? In a chain, what was, instead of that product, what did we have? If you have a chain, here's one node, another node, another node. So how many neighbors except I do you have for the node J? One. So here there was only one, the incoming message. All right? And what we do not have explicitly, right? And again, it makes no difference. We do not have this self-potential that is useful to incorporate basically evidence. Okay? So this was already there. This was only one term, and elimination of xj, the summation, plus the message j sends to node I. Okay? So if you want to compute, so when you do these calculations, let's say you are interested to go on and find the conditional of the root node given the evidence. In this case, so let me, because I see the calculation here, remind me when we wanted to find the marginal of any node, what did we do on a chain? When we wanted to find the marginal of any node. In the chain, there was left and right to every node, so what did we do? We took the messages coming from the left, the messages coming from the right. In general, trees will be whatever messages are coming, if we multiply, we get the marginal. Now, if I look at the root node only, any message coming from above? Root node. So all the message is coming from below. So basically, what you have is all the messages coming to the root node from its neighbors, from below, times, obviously, I have to put the self-potential of the root node, okay, if it is not 1. And then, if you want, you can normalize this the way you see on the denominator. Obviously, this equation you can apply to any node. So if you want to find the marginal of node I, you take the product of all the messages coming at node I from below and above, all right? And then just normalize it, and you will get the conditional of node I given the evidence. And actually, no, that's the same equation, okay? Well, it says here, use similar equations to find the marginal at every node. Okay? Now, the bottom line, and maybe I should have put this with red letters or something, coloring here, is that this algorithm scales linearly with the size of the tree. This is basically the best you can do, all right? Extremely fast, rapid, okay? And all the equations are exact. There is no approximation here. Okay, so we need to do, actually, we'll finish today doing different examples because they look trivial. Now, Suvik told me that in the homework, some of you, rather than doing some calculations by hand, you wrote little programs. Some of you wrote down, you summon this, and that should be the answer, right? The last one option is not a good one. You have to either write it by hand to do all the calculations or actually write a computer program to do this. But don't say, you know what? You multiply this, and then you sum, and whatever comes, that will be the answer. That doesn't help me, right? If I understood correctly, okay? Something like that. So let's say a simple case. We are interested here to compute the marginals in the simple tree. So obviously we're going to have some post-order elimination here, and this case will be this node and this and this and that. Okay, so we're going to start sending messages from the leaves all the way up to the root. So I can send this message up and this message simultaneously. And once node x2 has received these two messages, then I can send the message to the top to x1. You see that? Right? So we don't do this all at the same step, right? You send one message, this together, then you can send the messages. Once you have that, you can send the message to node 1. Once node 1 has received this message, then you can send a message back to node 2. All right? So, so node 1 sends the message M1 to 2, and then you are ready to do what now? Is this node ready to send the message to node 3? What do you need to send the message from 2 to 3? You will need to know all the incoming message, which is this, and this, which you calculated. So then you can send a message to, from 2 to 3, which is this message here. And then what do you need to send a message to 4? You need this, and you need that. So you can send a message to 4. So effectively, actually, once you get this message here, you can simultaneously start sending messages to both nodes 3 and nodes 4, as you see here. Okay? Once these messages are computed, you can go and calculate anything you want, the marginals, you can normalize, conditionals, you can put evidence, you can do anything you want. Okay? Now, obviously, when you program this, the tricky part is to be able to compute messages, not just one after the other, but we have some algorithm that says, you know what, I can compute this message simultaneously, then once I have all these messages here, I can compute the outgoing message, etc., etc. So you need sort of to have some way to figure out when a node is ready to send messages to its neighbors. All right, so is this a different graph? It's the same, different graph. Okay, so in this graph you can see the importance actually of having a protocol to send messages. Notice that here I can simultaneously send these messages that you see on figure B. Not one message, 4 messages all at a time. And I can do this, right, because this node, all right, can send a message there, right? The same here, the same there, all right? So on the second stage, I denote these messages with dotted lines to indicate that I calculated them previously. But once this node has received messages from the left and the right, what it can do, it can send a message to this node. And once this node here has received these 2 messages, you can send the message upwards. So on the last step, you notice, I make all these messages dotted because they calculated before. And if this node has a message from below, has a message already from the right, then it can send a message to this node. Similarly, if this node has a message coming in, has a message from the right, it can send a message to this node. Okay? So you get an idea that of what I mean a parallel protocol basically for sending messages. If you do this sequentially, obviously, it's not going to be a good algorithm, and for a big graph, it's going to be troubling. If you do this right, when the algorithm converges basically and gives you, converges, it's an exact algorithm. When it finishes, the cost will be 2 times the number of edges, because basically in every edge you have to send a message going and coming back, okay, as you see here. All right? So the number of steps basically the algorithm is 2 times the number of edges in your tree. I think I'm reading here, it says, be sure the algorithm never blocks. For a tree that will not happen, but if later on we will see other algorithms where you have loops, it's very possible you have an algorithm that keeps going and never ends. right? Keep sending messages and you have constantly on a loop, and you're in trouble. All right. So let me, I'm going to finish with this example because it's an interesting example. And this is the notation that I'm using is basically that of, the Markov random field that we used before, okay? So, we have pair potentials here. And if you want evidence, you plug in delta functions as, the notation is slightly different, but basically the same idea. So let's say root 11 is the, node 11 is the root, and we want to compute, we want to send messages first, right? And then compute marginals. And actually, let me see if we only want to compute what's going on at, okay. Well, there is no particular node of interest, but I will tell you what is specific to this example, right? So let's say we want to compute, this is the root node, right? And we want to compute all the messages sent on this graph. So we're going to do a post-order elimination. Can somebody spell for me what maybe a post-order will look on this graph? There are many orders of eliminating nodes, but here the optimal is the post-order. And you remember you start from the left tree and then from the left side to the right side. So potentially how the post-order elimination will look here. 1, 2. 1, 2, 3, 4. 1, 2, 7. All right, so 1, 2, 7, continue. 3, 4, 8, 9, 5, 6, 10, and 11. You see that? Okay. If it's of interest to you, what I suggest is you can look at the wiki and Wikipedia. There is 5 different types of ordering, but the post-order is basically what is used for variable elimination on trees. So this is what we need to use here. I mean, if you use something else, it's just the algorithm. The cost will be higher than using a post-order. Okay. All right. So here we're going to do calculations basically analytically. Okay. So, all right. So, we're going to follow this post-order elimination, and we're going to start to calculate messages, okay? So, I can calculate the message from node 1 to 7. Does this calculation make sense to you? There's no incoming message to node 1, so this is summation of the potential psi 1, 7, okay? I can do the calculation of 2 to 7 at the same time, no problem. This is. I can do the calculation of 3 to 8, 4 to 8, 5 to 10, 6 to 10, all right? So I can do the calculation of the first 2 lines all simultaneously on this graph. So now I need to calculate the potential from, the message from 7 to 9. And again, no equations are needed, right? So what you need to do is find all the messages that are coming to node 7, multiply with the potential between 7 and 9, and get rid of 7, eliminate 7. So basically, the message from 7 to 9 is this potential 7, 9. If you had, of course, the evidence for 7, you would put that in also. The message from 1 to 7, the message from 2 to 7. So obviously this requires that you already have done this calculation on the first 2 lines. Similarly, you can calculate the message from 8 to 9, okay? The 2 incoming messages times this potential and then integrating 8 out. And then, let's see, and then we need to calculate the message from 9 to 11. So this again, nothing special, the potential of 9 and 11. Where's that? Okay. The incoming message 7 to 9, the incoming message 8 to 9, and then integrating x9 out, and similarly the message from 10 to 11. So these are the messages coming from the leaves to the root, okay? Now, let me show you this sort of elementary way of calculating this message from 9 to 11, right? So basically, I'm going to solve this in a different mathematical form so you can get a sense of what this actually does, right? So the message from 9 to 11, effectively, we start with these nodes, we send information, and then we eliminate the 2, we send information there, and then we eliminate 2 nodes, and then from here to there, then we eliminate 9. So effectively, you know what we have eliminated to send the message from 9 to 11? Which was, can you tell me to eventually be ready to send a message from 9 to 11, you have eliminated what? You have eliminated lots of nodes, but these nodes together form what? Form the subtree that hangs on the left of node 11. You see that? I mean, all of these nodes is the tree that really, if you take node 11 and you hang it from there, all the nodes to the left of that is what you eliminate. So I can write this calculation of the message from 9 to 11, a summation on all these variables of this subtree, and I call this subtree the subtree that is derived once I remove edge 9, 11. Okay? So this is the tree that you get once you eliminate this edge from 9 to 11. Okay? So effectively, this is the message. This is what we have done. Now, what also this means, right, that this calculation that we had for the messages, you can start from this equation, all right, and rearrange the order of the summations, and then you can redefine again these messages that are propagating from 1 and 2 to 7, from 7 to 9, etc., as part of the summations. There's nothing really special. It's a way that you do the summations. So rather than doing the summations as one big equation, you do it in some elimination order, right, the way that is discussed here. So you don't go and do all of the summations in one equation. So don't write a computer program and say, go and sum on all of this because it's a trivial toy problem and that's the answer. You need to compute, you say, go through all these nodes in some order and start computing these messages, and when at each node this message arrives, compute the message outgoing from that node to another node, and when you get all of these things from the leaf to the root, then you are ready to go backwards. And here is backwards. The equations for backward recursion of messages identical to what we have seen before. Okay? So let me give you some of these equations. And I put these things in blue because I think the first time I typed them, not paying attention, I had missed a lot of these terms. All right? Because some of these terms you realized are messages that are coming from the right tree that comes out of 11, not from the left. So let's see. For node 11 to send a message to node 9, what do I need to know? When a node can send messages to any other node? What is the protocol that we discussed? To send a message... Okay, to send a message from 11 to 9, what is the protocol? When can 11 send the message to 9? When it only has received all messages from its neighbors. And the neighbors here, except 9, is node 10. All right? So, for 11 to send a message to 9, 11 needs to receive a message from 10. It needs to have not this message on here, all right? Obviously I cut and pasted the picture, but it needs the message that 10 sends to 11. All right? So basically, the message from 11 to 9 is this potential with the message coming from 10 to 11, and then node 11 eliminate. Similarly, if you want to compute the message 11 sends to 10, will be the potential of 11 and 10, and the message coming from 9 to 11, etc., etc. Okay? So let me see if there is anything here to finish. And so basically, if you want to see a physical sort of interpretation of the calculation we did for sending a message from 11 to 9, effectively, what you can envision is you look at the right subtree, all right? The subtree basically that you get when you eliminate the edge 9 to 11, all right? And then you do elimination of all the nodes in that subtree, okay? And that means you sum on 5, 6, 10, and 11 of the potentials corresponding to this subtree, okay? So if you do this, basically, what you will get is you will get this calculation at the end of the day, okay? But obviously, this is easier, way easier to remember. I don't have time to finish this 145, but what I suggest is look at the algorithms because they are recursive and they look a little bit sort of complicated. So the algorithm for setting the post order, it's a recursive algorithm that it's only 5 lines, okay? And it does this correctly, okay? The sum product algorithm that we described is basically a little bit different from the elimination algorithm, and it is recursive in nature. For example, collecting messages before you are ready to propagate, it's a recursive algorithm, you can see. Distributing messages from a node to the neighbors is also a recursive algorithm. So I would really like you guys to make an attempt to at least program something that involves inference on trees because it's sort of an easy algorithm. Okay? So, and as I mentioned, those who are auditing the course, if you don't really program these things, there's no way actually you will ever figure out how this thing works. Now, if